and it's a great pleasure to introduce Boris Zilber, who is one of the main contributors to modern model theory, and whose work is associated with this development of model theory towards applications in mathematics and connections of model theory with algebraic geometry, and work on Zariski geometries and Zilber trichotomy conjectures and principles are very well known. So we'll, in this audience, which is mainly Russian audience, there is of course no need to give a very extended introduction, but let me mention that Boris Zilber defended his PhD dissertation in 1975 in Novosibirsk, and then he worked in Kemerovo for many years in Kemerovo University, defended his habilitation or doctoral science thesis in Leningrad in 1986, and since early 2000s he is a professor at Oxford University, now Professor Emeritus. And, very welcome, and thank you very much for coming to us. Please.
Yeah, thank you very much for the introduction and for the invitation to this meeting. I took part in this series of conferences, logical perspectives, that I find very well, very interesting designed, and so it is my pleasure today. Well, actually, my talk is I cannot make a paper out of this talk. It is more like speculations, but I think it is. It might be of some interest. So these are the speculations that I tried in my conversations with my colleagues in Oxford and elsewhere, and so now I'm sharing it to this wider audience. Okay, and right. So how do I move? What I'm going to talk about is based on the analysis of applications, so that that logic in general, and of course I know much better what happens in model theory, so maybe I'm more concentrated on model theory. So applications that happened and are happening now in mathematics, in core mathematics. Some of them actually unexpected. Unexpected, not in the sense that you cannot expect this sort of result of this sort from this sort of people, but it is unexpected to broader mathematical community how on earth logic can help in solving problems in analytic geometry or number theory, if these are really serious problems. Now, as you see in the slide, my claim is that actually what is happening is a sort of a shift of paradigm of how mathematics is being done, combined with mathematical logic. And in my opinion, it parallels some shift of paradigm that happened in physics sometimes in the beginning of 20th century, when the observer became a part of physical model. What I just said it can be seen here in this diagram, that observer as a part of physical universe, and this is something that, of course, was introduced both in relativity theory, that in Einstein's theory, but also, of course, in quantum theory, which are long way from relativity theory, but for some really serious reasons, the observations in quantum theory have impact on physics, and the same actually things happen in wider fields. Well, maybe I'm going to go too far from the subject of today's talk, but even in the arts, the painters of the second part of 19th century and the beginning of 20th century played with the idea that the object is not something fixed. If you want to paint an image of an object, it depends on what is your vision of the object, and what is your perspective from where you look at your object, and this becomes a part of art. So it is some sort of a parallel developments in a global change of paradigm in the way that we see nature around us. And so now what we see is happening is that observer becomes a part of mathematical universe, and that's what I'm going to argue about. And the way that observer enters mathematical universe is by focusing on the language in which a certain part of mathematics is being considered. That, well, maybe as an illustration, I should give you a historic example that so once mathematics learned about complex numbers, so there is such a thing as a theory of complex numbers, which is clear enough for mathematicians of 19th century and as a matter of fact also 20th century. But if we look closer, then some people work with complex numbers, seeing the field of complex numbers, which of course means that we see certain algebraic relations, the addition and multiplication, and ignore everything else. Then, of course, there is something else. It is the same structure as a field of complex numbers, but now we take into consideration metric, and then it becomes a huge difference. And actually, quite recently, it was a discussion with very serious group of mathematicians that are coming from differential geometry, and it was mentioned that such thing as automorphisms of the field of complex numbers, and these people they just couldn't understand what we are talking about, because for them the only automorphism of the field of complex numbers is complex conjugation. And this, of course, is that the point of view on complex numbers is different from what meaning we put in the definition of the field of complex numbers, and this has a huge set of automorphism due to Schreier's theorem of the beginning of 20th century. Then, of course, we have Gaussian integers, and this is a part of number theory. We have a function of complex variables. It is another branch of mathematics, and we have theory of residues, contour integration, and similar things, which is well, probably topology, algebraic topology, and this is all what mathematicians usually mix it. And so what we actually what is the difference with the analysis coming from logician is that we want to know exactly in what language we present the structure of on complex numbers, and what is definable and how it is definable. So by what sort of formulas it is first order formulas, or high order logic is being used, and so on. And each of these choices can be seen as a change of the observer. So it is observed from a different point of view. Well, now you see this. This was, of course, understood at some stage by mathematicians, and we, at least my generation, was educated on this Bourbaki style notion of structures, but many people working in many areas of mathematics just ignore this sort of formalism. However, it is very important, and it is useful, and that's what I'm going to try and prove. Well, as you see here, it is also comes very close to this point of view on what has changed in paradigm of mathematics. It is also a very productive and quite similar point of view that uses category theoretic approach. And this category theoretic approach became also a very powerful and very broadly accepted tool, as broad as mathematical physicists and I think even hardcore physicists do have a very good are very fluent in the language of category theory. So, in fact, this is included in, well, implicitly included in my discussion today. Oh, this is empty. Okay, so what does it bring really into mathematics, and how it becomes efficient as a tool of mathematics? Well, the first thing is that it brings us the new ways of understanding infinity and limits, and this is, of course, is through first of all set theory, this very classical part of logic. Then also widely known non-standard analysis. This would go into understanding of limits and understanding that it is a sort of course, a non-standard model where finite becomes infinite. So we have, for example, infinite natural numbers in non-standard arithmetic, and this is some step into in this sense infinity can have structure of a natural number. Then well, it is quite close to non-standard analysis, technologically different area of mathematics of limits. It is pseudo-finite structure. So if finite structures to the limit, then an infinite structure, but now it is an infinite structure with some finite characteristics, and it was productive to analyze these structures logically, model theoretically. Now, the more recent developments is in classification of mathematical theories with respect to the language and structures. And the, of course, what was very popular in 1950s, 1960s, the classification was on the basis of algorithmic decidability, and maybe later by complexity theory. So you can say, for example, that certain class of structures like groups, they're very complicated or less complicated in terms of, well, their theories. In terms of algorithmic decidability, and this gives you some classification pattern, and you can say in this classification pattern that so here we are with a tame class of structures, and this class, well, okay, if you believe that this class of structure is tame, then you can go there and find something mathematically interesting that can be applied further, maybe. Right, so it is then we have this the more recent developments, which started in since Morley theorem, so it is the second part of 1960s, and further mightily developed by Shelah and others. So it is stability theoretic classification theory. Actually, what happened, in my opinion, as far as model theory is concerned, is that it just turned out that classification of structures or theories by algorithmic decidability could be a good thing, but this other principle of classification is better in many respects, and something that is tame from this point of view is usually tame also from this point of view, but not the other way around, because for the simple reason that you can have something that is algorithmically decidable, and you throw in some constants that maybe you order them in, or something you do about these constants, and this would change the decidability status of your structure, which doesn't happen here. But maybe more important is that this is based, this Shelah's classification theory, based on started from, as I mentioned, started from Morley's categoricity theorem, the great categoricity theorem, and its guiding principle is that you see, categorical theory is where your language is adequate to your structure, where you can describe your structure up to uniquely up to isomorphism in terms of your language, and this is a very powerful principle. And what goes further with this classification theory is that then you weaken this relationship between the language and the structure, and so it is. It is. So if you believe that, like I do, that categorical structures are in the center of mathematics, then you extend your classification around the center, and so you classify tame and slightly less tame structures, and as a result, what we have now is almost something that looks like Mendeleev table of elements, and I would say is as useful as Mendeleev table of elements. So it is a really big development in model theory, and I believe also in logic as a whole. And it also brings in very powerful geometric vision in model theory and logic. And then separate from this, and from this, although again related both to this and this, is the theory of minimality. So very shortly, or minimality is starts from understanding that the real numbers, the field of real numbers, is very nice theory, and it is indeed. Although this theory is not stable. So the classical object here is the field of complex numbers, or more abstractly, algebraically closed field. And so the whole of absolute algebraic geometry falls into this classification theory. And then later, in more remote areas of this classification table, you can see also something that is more like arithmetic algebraic geometry. But the minimality theory is based on the reals, which are not stable, and but the principle of tameness in minimality is somewhat different. And in fact, in the original stages, it was copied from the approach from stability theory by Pillay and Steinhorn. And then it was application of some finding in real algebraic geometry that extended very much the class of known or minimal structures. It is a work of Gabrielov, and later a lot more of transcendental functions found to be working well with the real analysis. So it is real analysis together with classical transcendental functions that turn out to be the class of structures that have minimal theory. And applications of this. So when in my first slide I mentioned strong applications, what I had in mind is what I know better are the applications of in this area. So it is mainly to algebraic geometry with extensions to well, it is algebraic geometry combined with say p-adic analysis.
Excuse me, Boris. Did you change slides from new ways of doing maths, or what?
No,
exactly?
No, I'm still on this slide.
Okay.
Yeah, I'm sorry. It is. I'm using my voice more than my pictures. Okay.
Okay.
Yeah. So. So they and this was going for some time. It was also very successful applications of minimality theory, but recently some started something that started about 10 years ago. It was just a huge explosion in this area, explosion of interest to this area from mathematical community. It is when Jonathan Pilla, so with Pilla and Bombieri, they found some interesting method of counting a number of rational points on an analytic surface, or something like so you have something that is given by analytic equations, and you want to see how many rational points are in a certain domain of this analytic variety. And but this was of very restricted, so couldn't be applied to interesting situations because it was well, some very basic observation. But then Pila, who actually was just a number theorist with some vague interest in logic, but by that time he already knew some of minimality, the idea that this could be extended variety, but with tape could be properly defined in terms of minimality, and this indeed worked. And now we have literally hundreds of young people who work in this area, who learned logic and use all this terminology of definability and similar things. So it is indeed very applicable. Yeah, this whole thing, classification theory. Well, actually, I can say similar about this. The study of pseudo-finite structures, actually combined with the ideas from here. Right now. So as I said, that it is all based on simple principle that we should look at mathematical structures, having in mind that we observe it from certain position in a certain formal language, and we don't want to go out of the language, and so we want to learn what is definable inside the language, and this is a point that proved useful. But as you see in this slide, if you work within this context, then of course you have you risk to encounter the problem of, as we know from classical studies in logic. Because I'm trying to speak in terms that parallel physics, so the comparison, the appropriate comparison here is that there are self-reflection paradoxes, well-known paradoxes in physics. Well, first of all, it is the measurement problem, which literally means that that once you perform the act of measurement on a physical object, you actually change the object. Well, it is you cannot see it if you do it in a macro world, but in micro world, in the world of quantum physics, this is a real problem. Something similar is the uncertainty principle, far from being a full list of this sort of strange behavior of the quantum world. and strange behavior also of relativity world, like this black holes probably also fall into this category. Now, the thing that I also like to mention is that the self-reflection is also a feature that is known in financial markets, and the effect is quite similar. You see, if the problem with financial markets, a mathematical problem with financial markets, is that once you it can to agents of financial markets, then the market changes the market, and the theory of financial markets. And there is actually some interaction between the ideas in the study of financial markets with the ideas in quantum physics. And one of the basic equations, Black-Scholes equation in the theory of financial markets, is a close analog of Schrödinger equation from physics. Now, since self-reflection also happens in physics, so physics is a very successful science, and it has developed tools to deal with this effect, and these tools are it is understanding that the algebra of physics should actually be non-commutative, and it is not just a philosophical principle. It is a very concrete computational tool, which I believe was introduced by Heisenberg. It is a so-called canonical commutation relation, and well, so the way that it was introduced and then discussed, it is really dramatic and then probably great lesson to sciences. So it was, I believe, 1927 paper that was called later the magic paper of Heisenberg, where he simply realized that to get a right, to calculate correctly effect of certain physical process, black hole radiation or something, you should use this principle that when you change the order of your symbols, so position and, well, this is position and this is momentum, when you change the order of application. Yes?
Boris, apparently you showed us something on the screen, but our screen is frozen, so maybe you can just
is it frozen now?
It's still frozen.
Oh, okay.
Yes. Yeah.
Okay.
Okay. Very good. I have the
Yeah.
impression that we missed quite a few of your slides, in fact, but never mind. So,
but you have seen this one?
no, actually, no. It was frozen at some point, and at slide number 7. So basically, everything. But nevertheless, I think we remember what you said. So this is
okay. Okay.
It was the fourth number 7.
Yes, number 7. Yeah, I think that number 7 is this one with
yes.
With classification theory or minimality and yeah. Okay. Right. So I do continue. Now we have, so I repeat quickly, we have, once we have observer, we have a problem of self-reflection, and it has a certain form in certain forms in physics, and it also is an issue in the theory of financial markets, and now we are talking about the way that the physicist has resolved this problem, and this is through understanding that the order. So in the algebra of physics, the order of the variables. First of all, position and momentum matters. So when you change the order, you have to take into account that there is a small quantity that you have to add or subtract, and this just turned to be the right recipe for calculation without really understanding of why it works and what is behind it, and of course it generated a lot of discussion and a lot of questions, and the paper itself, the paper of Heisenberg, was called at the same time the greatest paper and ugly for this reason. And then later, it was so this phenomenon was understood better, and physicists use this image for explanation that points have structure, or in more mathematical terms, one would say that physical space is fibered, and again, even more mathematical terms. So you encounter something that is in geometry is called principal bundles. So you have a certain kind of a base as your space, and then over the base, over each point of the base, there is a fiber on which a group acts. And so this are principal bundle. This is called principal bundle, and it is already present in quantum mechanics, but a more developed form in gauge field theories. And so I have well, these are slides from many years ago, where I demonstrate so how it can work. Yeah, maybe I should use rather. Yeah, so you see, so it is it is a classical space, but in fact every point over it should be seen as not so it is a fiber. So in this picture the fiber has just 2 points over it, but in reality it is a whole infinite fiber. I mean, in physical theories, we don't know about reality. So it is infinite and even continuous fiber over it. And so what we see in the picture below is this, but when we look at the picture above, it is actually so the same picture can be well the same point. So if you are inside it, sort of trying to understand what state of mind this point has, so it can be in this state, or it can be in this state, or if this fiber is bigger, then many more states for something that is visible to us as one point. So that's what is believed what happened, and this is the appropriate geometric picture. Now, so apparently the same non-commutative effects are happening in logic, and one can say that the observer that reflects on his own state, by this reflection changes the state. As an example, here is this classical Berry paradox that reads as the smallest positive integer not definable in under 60 letters. So it is it gives you some definition, and actually, so it seems to be using the accepted language, but in fact, you see in this definition, by formulating this, you somehow raise the level of your language. That this is actually very tricky expression that wouldn't be used in ordinary language. Of course, in this paradox, we assume that we work with a natural language, and this sort of expression do not happen in natural language. In fact, this is called Berry's paradox because, as I learned, so Russell well lectured somewhere about logic, and this this guy Berry, he was a librarian in the main Oxford Library, and he came to a few days later. He came to Russell and suggested this this definition. So he invented this. This is not a natural sort of notion. And by inventing this, you sort of change the status of your language, and so now you are not the same observers that you were before. You sort of move to the next level. Well, anyhow, this is my interpretation, or I'm trying to think in these terms. And if you look at similar paradoxes in a more formal language, like in the language of set theory, well, it would correspond to the set of all sets. Well, it is similar effect that when you say the set of all sets, you mean that you have a method in the taking it in more intuitionistic to go through all your that here that you have a method to go through all definitions that are up to 60 letters long, and hierarchy. And to me, it sounds quite similar to what happens in this non-commutative picture of physics. And so finally, my guess is, well, it is actually a question more than a guess. I don't know enough to claim anything here, but what little I know, it looks that homotopy type theory is sort of combining these two understanding of how to deal with these paradoxes, and in many ways it is a similar picture, the picture of non-commutative geometry that arises in these beautiful constructions of homotopy type theory. Yeah, okay, so these are my observations about logic and model theory and how it interacts with mathematics as a whole. Thank you very much.
Okay, thank you very much.